Hi, everyone is joining. We're just waiting a couple of minutes for people to get on, and we're also going to start a live stream on YouTube. So we will start in a minute, and as people are doing, just say hi in the chat box and where you're from.
Okay, I think we are now live on YouTube.
Great.
And I will hit the record button and I will go on mute.
Okay. All right. Well, hi and welcome everyone. This is Karen Haug from University of California at Berkeley. It's Solar Week this week, and that's where solar scientists answer your questions about the sun and about life as a scientist. And you can find that at www.solarweek.org. Welcome to our Solar Week live webinar featuring Dr. Claire Raftery. Her talk today is called Caramel Corn or the Sun, what's behind the best picture of the sun we've ever taken. This webinar will last about 30 minutes, and you're encouraged to ask questions along the way in the chat box, which I will relay to Claire. Your microphone is muted and your webcam is off. You can also ask questions on Solar Week itself through the end of the week. And this webinar is being live streamed and recorded. So Dr. Claire Raftery is currently the head of education, outreach, and communications at NSF's National Solar Observatory and for NSF's Inouye Solar Telescope in Hawaii. Dr. Claire was born in Ireland and started her career as a solar physics researcher. She's always been excited for sharing the wonder of science and started her work in science education and communication with Multiverse at UC Berkeley's Space Sciences Lab almost 8 years ago. She's been leading the team at the National Solar Observatory since 2016 and is excited to share innovations from the Inouye Solar Telescope as the telescope comes online in the coming years. Welcome, Claire Raftery.
Thank you, Karen. Can everybody hear me okay? I hope so. Okay, well, let's get started. So today I am here to talk about whether the sun is made of caramel corn or of something else. I'm hoping that you all saw these pictures. Which one of them we'll discover in just a few minutes. A few weeks ago when we released the first pictures from the NSF's Inouye Solar Telescope. And today we're going to talk a little bit about what's behind them, how we took the pictures and the science behind these pictures. So as Karen mentioned, my name is Dr. Claire Raftery. I'm the Director of Education, Outreach and Communications for NSF's National Solar Observatory, which is the organization that's leading the construction and operations of the Inouye Solar Telescope in Maui, Hawaii. I also want to give a very special shout out today to NSO high school student intern, Catherine, who helped me put together the presentation today. She worked with us at NSO a few weeks back. So thank you, Catherine. Okay, so this is the picture. This is the picture, the first images from the National Solar Observer or the National Science Foundation's Inouye Solar Telescope. This is a subsection of the surface of the sun, but there's a lot going on here and we're going to try and unpack some of this today. But before we do that, I want you all to take a second and in the chat box, I want you to tell me what it reminds you of. What do you think of when you see this? When we release these pictures, we got all kinds of things. We got honeycomb, we got fish scales. It just reminded people of lots of different things. So tell us in the chat box what you see when you see this picture. So cheese, plasma, brain, that's a good one. What else do you see?
The desert and parched land.
Oh yeah, that's good, yeah. Like a picture from space. Scales, scales up. Lava lamp bubbles. That's a good one, actually. The lava lamp bubbles is that's going to be a little bit closer to home than some of the others, but they're all great ideas.
Little flakes of gold. That's what I thought myself. Half formed colored brown glass, linoleum or epoxy floor coating, popcorn.
Definitely caramel corn. That's true. So yeah, these pictures, they look like a lot of stuff that we are familiar with here on Earth. And I think that's part of what's so interesting about them, is that this thing that's so far away, this is happening on the surface of the sun, and yet it looks so familiar to us. We can draw conclusions and analogies to our very own life here. So let's unpack this a little bit. So what is it that we're looking at? Well, this is, I'm going to try and put this in context a little bit. So the yellow ball here, this is a picture of the full sun. This is from our other telescope called GONG, and this is taking a picture of the full disk of the sun. Now, the Inouye Solar Telescope can only see small parts of the solar surface at any given time. So this little box in the center here, this is about the size of the image that we see from the Inouye Solar Telescope. So this movie that we saw a moment ago is actually only about this size and the full size of the sun. But because the resolution of this image is so good, we're actually able to zoom in even further and take an even closer look at what this image is showing us. So this is zoomed all the way in. So we're using big numbers here, but I'm going to try and put them in context in a few minutes. So this box right here is about 7,000 kilometers, or just over 4,000 miles tall and across. So it's 7,000 kilometers square. But that means that this picture is the highest resolution image of the sun's surface that has ever been taken. And we see things in this picture that we've never seen before. This feature up here that looks a bit like a maple leaf, we've never seen anything like that before. And all down here, these detailed features, in all of the past pictures that we've taken, these have been blurred out. They just look like white blobs. We don't see any structure. And this is what we're really excited about when we see these pictures. So to give you an idea of what the scale actually means here, we have two comparisons. So this box up here on the right-hand side, this box is about the size of the entire state of Texas. So just to give you an idea of how huge that actually is, because it looks pretty small in these pictures, especially if you scale back to the full picture of the sun, you can barely see one of these little specks, but that's the full size of Texas. And then the smallest things that we can see, about the size of these specks over here, that's about the size of Manhattan Island. So let's put that in context. What does that really mean? So if we take Manhattan Island, so that's this plot right here. This is an outline of Manhattan, and we scale this on the size of, relative to the size of the whole planet Earth. So if we put this on the size of the whole planet, and we see what this means. So I want you to keep in mind how tiny that Manhattan is compared to the whole size of the Earth. Now, if we take that and we put it in context of the whole solar system, think now about how small Manhattan would be. So if we flip it around, and if we were sitting at the sun with a telescope and we were trying to see Manhattan on the size of the Earth, which is 150 million kilometers away, that's really, really very small. And so that's how small the features are that we're now able to see on the sun. We're just flipping it around. We're sitting on the Earth with our telescope, and we're able to see features as tiny as Manhattan on the surface of our sun. So what does that mean? Well, if we go back to our picture, we see all of these bubbling, moving, all this motion happening. And it means that these bright areas in here, in between these big cells that we call granules, that means they're about the size of Manhattan Island. So that's how the scales, even though these are the tiniest features that we can see, they're still the size of all of Manhattan. They're about 25 kilometers, or about 13 miles in length. And that's, we're talking about really crazy numbers when we talk about the sun. Okay, but what is it that we are seeing? All right, so back to the chat again. I want you all to chime in on this. What do these three videos have in common? On the left-hand side, we have a video of some miso soup. In the middle, we have the picture of the video of the surface of our sun. On the right-hand side, we have a video of a concoction of vegetable oil and glitter, just to show the motion in the vegetable oil. So what do you see when you see these three things, and what do you think they have in common?
Someone, well, we see guesses like heat, convection cells, chaotic motion, cracks.
Yeah, so I see a few of the right answers.
They all move.
They all move. Okay, so I saw a few people with this answer. The correct answer here is that they are all experiencing convection. So convection is one of the three ways that heat can be moved, transferred between different surface or different areas. And the three of these are experiencing convection. So the next time you have some miso soup, before you eat it, just pause for a second and watch it, and you'll start to see all of these lovely patterns as the soup just transports energy as the patterns move around, and you can see convection for yourself. So the same behavior that's happening in your miso soup is also happening on the sun and happening in this demonstration that we put together here that has oil and glitter in it. So where else do we see convection? So back to the chat, where else on, let's say on planet Earth, do we see convection? Or if you see it elsewhere, not on Earth, that would also be interesting. I'll give you a hint. It's a really important part of our sea life. Clouds, yeah. Ocean currents, excellent. Currents, yeah. Campfires, anything with heat rising, yeah. So anytime that we see heat transfer between liquids and gases, that's when we start to see convection. So what is convection? This is a video that I found on YouTube, and the credit goes to Science Up with the Singing Zoologist. So thank you for sharing this great demonstration. This is a video that shows the development of convection. So in here we have this is basically a glass bowl filled with water, and there's some red and blue food coloring at the bottom of this. And then it's being heated from below by this cup. And as you can see, over time, we start to see this motion of the water, in this case, moving upwards, and then it gets pushed outwards, and then eventually it starts to double back on itself to create like a circle. And so what happens is the water near the cup where the heat is being originated is getting warmed up, and it starts to rise. And then it gets pushed out of the way as more rising water shows up behind it, and it starts to lose its heat then. And as it starts to lose its heat, it then starts to sink, and it comes back down to the base again, and it moves back in where it gets reheated. So we get this cycle, a cellular rotation going round and round in circles. And this is exactly the same behavior that we see on our sun. The difference is with the sun, of course, that we're looking at much, much bigger cells than we see here. This is only, a few inches across. With the sun, we're talking about, hundreds and thousands of kilometers across. So let's have a look at what that means and how this comes into play with our sun. So this is a cartoon of the inside layers of our sun. And we start with the core. So inside the very center of the sun, heat energy is generated from nuclear fusion. So the sun is powered by this nuclear process inside the core. And once this energy is generated, it then has to escape the sun, it has to leave. So first of all, it has to go through a very dense region called the radiation zone, which is this sort of stripy area just above the bright core. And so this area is actually so dense that it takes about 1 million years for an energy particle to get from the edge of the core to the edge of the radiation zone. Even though it's not that far, it's certainly not millions of years distance far, but it takes light particles that long to get to the edge of the radiation zone, because every time it moves, it bumps into another atom and it loses some of its energy, and then again. And we call this a random walk, so that it takes a very, very, very long time for energy packets to escape from the core to the edge of the radiation zone. So once our energy has finally reached the edge of the radiation zone, we get into this convection zone. This is what we're interested in today. And so this is where the sort of the chemistry of the inside of the sun has started to change enough that the gases can actually move up and down. And so this is where we see heat from the bottom of the convection zone, the plasma at the bottom of the convection zone being heated up by all of this heat energy coming from the radiation zone, from the core. and then it rises out towards the surface of the sun where it starts to lose its heat, and then it cycles back down to get heated again, much like the video that we just saw in the previous slide. And we call these, on the sun, we call these giant loops granulation cells. And so these granulation cells, we see the very top of them down here on the solar surface. So they look a bit like this. Oops. There we go. So yeah, we see the top of these granulation cells. So in this picture that we have here, we have the heat that's the heated plasma coming up towards us, and then it starts to lose its heat, and then it cycles back down. So we see the stuff coming towards us is seen as little bright areas. So the center of these cells. And then the dark channels around the outside, these are where the plasma is starting to fall back down into the sun so it can get reheated and come back up. And so we have this big circular pattern. Now, I want to just remind you about the size that we're dealing with here. So we said earlier that one of these convection cells is about the size of Texas. So this picture is not quite to scale on the sun. I've just pasted it in, but one of these is about the size of Texas. So that means that the plasma is coming up in the middle of Texas, and then it takes the whole dimension of the whole state to go back down again. And that's how big those cells are. So these are really, really big. So that's the inside of the sun. That's how we get energy from the inside, and that's how we form those granulation cells that we saw in those first pictures that we got from the Inouye Solar Telescope. But there's even more exciting things that this telescope is going to be able to show us in the near future. So we have 5 different instruments that the telescope is going to have, and we've just turned on one, but we have 4 more to come on online in the next year. And the most exciting one, in my opinion, is one that is going to study the solar corona. And no, I don't mean the coronavirus. This is not the same corona. We are talking about the solar corona, which is the region of the solar atmosphere that we see during a solar eclipse. So if you saw the 2017 solar eclipse in the continental USA, maybe give a shout out in the comments. Or if you're elsewhere in the world and you've seen a different solar eclipse, tell us when it was and where you saw the eclipse and what you thought when you saw the eclipse. So we can see here, in this picture here, these are 2 photographs that we've put together. The picture in the middle, this is a picture of a special kind of picture of the sun's surface, where we see magnetism. So the black and white spots here, these are parts of the sun's magnetic field. And all of this stuff out here is also because of the sun's magnetic field. So if you've ever played with magnets, maybe you've had 2 magnets and you try to push them together and they don't go together, they kind of repel each other. Or if you have them oriented a different way, maybe they stick together and they're hard to pull apart. If you're very unlucky, you've cut your finger in between 2 very strong magnets. That's not fun. It's quite painful. I don't recommend it, but it tells you how much force there is in between 2 magnetic field lines. And so all of this stripy and loopy striations that we see in this picture in the solar corona, these are all as a result of the sun's magnetic field. And so if you squint and use your imagination, you can see that these look like the same sort of field that if you've ever played with magnets and iron filings, if you put a magnet down and then put a sheet of paper over it and sprinkle some iron filings, you see a kind of a butterfly pattern. And so we can see the butterfly pattern sort of showing up here. So it comes out of the top of the sun, around and back in. But there's all of this stuff around here along the sides. This stuff around here that definitely doesn't look like a butterfly pattern. But what actually happens is this is where the sun's magnetic field is getting all tangled up on itself, and it's the source of all of the solar explosions. So solar flares and coronal mass ejections, everything that we call space weather is all as a result of the sun's magnetic field. And so the Inouye Solar Telescope is pretty much dedicated to better understanding the sun's magnetism. All of the other 4 instruments that we have all have special techniques to be able to see and measure the sun's magnetic field in ways that we haven't done so before. And so this is a really exciting time to be involved in the scientific exploration of the sun. So the kind of things that we're going to be studying, you can see in these 2 videos. So we'll start with one video here. So let's do another quick chat discussion. So I want you to jump on the chat window and tell me, what can you see in this video? What's what are the first few things jump to your head when you see this video? Solar flares, explosions, yeah. What else do we see? Looks like the sun cracked. It does. It looks like the sun just opens up at the top, and yeah, coronal mass ejections. It looks like propulsion. It definitely does. Bright spots. Solar flares. A duckling. Yeah, I guess it looks like a duckling. How about this one? Let's look at this one. Let's try again here. So what do you see on this video? Sunspots, yeah. Sparkles, loops, explosions, yeah, they're all very good. Lights. Holes for, where is that? There was one here that was good. I can't remember. Holes for solar wind, I think it was, which is very good. That's these darker regions here are called coronal holes. So the thing I love about this video in particular is watch this part on the right-hand side here. So wait till it restarts. Once the video starts again, you'll see that we have a big explosion called a solar flare. And then you start to see a ripple that moves the whole way across the sun. Now, bearing in mind that the Earth is tiny, the Earth is smaller than this, you know, one of these active regions, one of these bright spots here. Think about how huge that wave needs to be able to ripple across the entire solar surface as it moves all the way across. And so this tells us that the sun is one big system. It's all interconnected. It's all moving and evolving it together as a one big system, and that we have to understand all of the system to be able to fully understand what's happening. So these explosions are driven by the sun's magnetism. And so understanding what causes them and trying to figure out if we're able to predict them, which is really where we all want to go at some stage in the future, is really important to scientists. So this is a really exciting time for solar physics, actually. So some of you may have heard about NASA's Parker Solar Probe, which launched in 2018. And this is a probe to study the sun as well. There is a similar mission called Solar Orbiter, and it's also on its way towards the sun. And these two satellites are going to move, they're going to travel towards the sun and be able to study it up close. And meanwhile, the Inouye Solar Telescope is going to keep an eye on the big picture of the sun and really drill down into the detail of what it can see, what the magnetic field is doing at the same time. So these three missions are working together to be able to piece together that whole big system that we mentioned, the ripple effect moving across, and how not only does it affect the sun, but how does it affect space, and specifically, how does it affect the Earth? That's what we're really interested in. So let me tell you a little bit about the Inouye Solar Telescope. This is a telescope that is almost finished being built in Maui, Hawaii. We are still technically under construction through this year, but we are very nearly ready for operations, which means we'll start taking pictures of the sun and data from the sun on a regular basis. So this is a picture that a cartoon that we put together to sort of go into some of the detail of this telescope. So if we zoom in a little bit, we can see here the light from the sun comes into the telescope, first of all, through this hole in the dome. So this outer area is called the dome, and we have a hole here called the aperture. And the light comes through the aperture, and first of all, it hits our primary mirror. And this mirror is really the linchpin of the telescope. This mirror is 4 meters, which is about 13 foot across, which is significantly bigger than any other solar physics telescope that has ever been built. So to put it in context, the next biggest solar telescope mirror is 1.8 meters. So we're at 4 meters, and this is at the next biggest is 1.8. So this is significantly bigger. Now, as you can imagine, gathering that much light from the sun and focusing it onto a single point, that poses a lot of challenges when it comes to heat, because you have all of this solar radiation, we're focusing it onto a single point, and we got to make sure that the telescope doesn't go on fire or that we don't damage any of our optics or our cameras. We want to make sure that everything is very well controlled and that we keep everything as stable in temperature as we can, because what we don't want to happen is for there to be lots of fluctuations in how hot the telescope or any of the telescope components get, because if we get a lot of changing heat, then we get aberrations in our pictures. So if you've ever been driving on a hot asphalt road, or sorry, on an asphalt road on a hot day, you may have seen sort of a shimmery effect on the road, a mirage it's called. And similar things can happen in our pictures if we are not careful, if we don't control our temperature. So our engineers have put an awful lot of effort into making sure that the whole telescope is very well thermally controlled. And a big part of this is the next point on our journey, and this is called the heat stop. And so the place right before where all of the light gets focused is where we put the heat stop. The heat stop is basically a donut-shaped piece of metal that can be actively cooled. So the light passes through this, and any excess heat gets pulled away by the metal, by the cooled metal, and it means that we are able to keep an eye, very close eye, on how the rest of the heat gets passed through the system. So once we get through the heat stop, we hit the secondary mirror, which is also in this little box up here. And then the light starts to make its way down, make its journey down through the rest of the telescope. So there's a series of mirrors in this area here that help to bend the light from this angle downwards. And once we go downwards, the light reaches this very special platform here. So this is called the Coude Lab, and it's basically our instrument laboratory. So in this cartoon, each of these circles here represent a camera, a specialized camera that we have. So we have 5 specialist cameras in this room right here. But what's really interesting about this is this whole room, which is, it's 150 tons in weight, but the whole room rotates independent of the building. So the building stays still, and then this whole room rotates inside. And the reason that happens is as the sun passes overhead, it doesn't pass in a fixed position. It looks as if it's rotating across the sky. And so if you're taking really, really high quality pictures of the sun as it passes overhead, but it's rotating, then your pictures are going to be all blurred. And so the best way to solve for this is to rotate the cameras under them. So as the sun rotates, the cameras rotate with it, so it makes it look like the sun is staying still. And that's how we can take really, really high precision pictures of the sun throughout the whole day. So in this room, or just off this room, you can see this window right here, and this is where our telescope operators sit. So these are specially trained technicians who know all of the different details and how to operate this huge facility. And they're able to tell everybody, or they're able to give all of the commands in what needs to happen and when it needs to happen. And they're also very important in making sure that everything remains safe and that everything remains stable in the way it's supposed to be. So they're able to see all that's happening in the instrument room as this is going on. So this is where the pictures that we released, that we saw a few weeks ago, this is where they were taken. The light came through the telescope, down through all of these systems that help to make sure the light is prepared and ready for the cameras. And then the light was fed into one of these cameras called a visible broadband imager. And this is where these beautiful pictures came from. So I'm going to jump real quick to the other 2 missions that I mentioned earlier, NASA's Parker Solar Probe and the European Space Agency's Solar Orbiter missions. So I mentioned that these were 2 satellites that were moving towards the sun. The Inouye Solar Telescope is a ground-based telescope, so it's located on Earth. One of the great things about being a ground-based telescope is we can build this huge mirror. We have this 13-foot mirror, which you can't put into space. But what you can do in space is you can leave the Earth. So these 2 telescopes are moving through space towards the sun. And together we're going to basically have three pillars of observations to be able to see what's happening with the sun's magnetic field all together and study the sun and what's changing. So this is a nice little animation that shows the evolution of the orbits of these 2 spacecraft as they approach the sun. So we have the planets moving here, and then this turquoise color is Parker Solar Probe. You can see that it sort of swings by, it flicks by the sun, and it gets very, very close into the sun here. Meanwhile, we have the Earth rotating around the edge in the sort of purple violet color, and that's where the Inouye Solar Telescope is. And then we have this grassy green color, which is Solar Orbiter, which is the European Space Agency telescope. And so all of these instruments together are going to be able to really piece together what's happening on the sun with its magnetic field like we've never been able to do so before. So it's a really, really exciting, an exciting time to be involved in solar physics.
Excuse me, Claire. There were a number of questions about getting close to the sun. I think that's something that would be great to explain, how close we can get without our usual understanding of imminent vaporization.
That's a great question. So let me fast forward this a little bit till so right about here. So the Parker Solar Probe is able to get 90% of the way, I think it's like 94 or 93%, I can't remember exactly, of the way from the Earth to the sun. So it gets really, really close to the sun. Solar Orbiter doesn't get quite as close, but what's different about their orbit is instead of going around the equator, they're actually going over the poles this way. And so Parker Solar Probe will be able to see at the equator, the Solar Orbiter will be able to see at the north and south poles, and then the Inouye Solar Telescope is looking at the entire system. So I think Solar Orbiter gets to about 30 solar radii. I actually can't remember what the distance is. It's a little bit further away from the sun than the Parker Solar Probe is. Let me see if I can, so you can see here's the orbit of Parker Solar Probe. And as you can imagine, there's an awful lot of engineering that has to go into this. So we talked a little bit about some of the heat protection in just looking at the sun from the Earth and what the Inouye Solar Telescope has to go through in order to protect its optics. An even more rigorous process needs to happen with Parker Solar Probe and Solar Orbiter, because they're actually approaching the sun. So as they do that, one of the biggest challenges that they have is as you're facing the sun side is going to be very, very hot, but they have huge heat shields, but the side pointing away from the sun then is very cold. So you have this huge temperature difference on just the one spacecraft. And so how do you make sure that the different spacecraft or the different elements of the spacecraft are protected and that they are not damaged by this changing temperature? So using their heat shield is a really key part to being able to protect them from the heat coming from the sun. I saw a question earlier, is this in real time? It's definitely not in real time, it's sped up. So it is starting, I think, in 2018. This halfway point is 2025, and it goes all the way till probably 2030. So it's about 12 years worth of simulation. So it goes much, much slower, but we don't have time for that in this presentation. So I sped it up to be able to see it better.
Yeah, speaking of time, we're about time to start wrapping up, but you can also put your questions over on Solar Week, which is again www.solarweek.org. I don't know if you want to answer maybe one more question, Claire, or I know we've passed our half hour.
This was my last slide, and it's really just gratuitous beauty shots of the sun and all solar explosions. So I'm happy to take questions now. I see one here in the chat window. How big is the aperture in the Inouye dome? The aperture is 4 meters as well, so it matches the size of the mirror. So it's keeping a very well constructed beam of light coming into the telescope. How many Earths can fit into the sun? I can't remember the exact number in the whole volume of the sun, and it's certainly many. I think it's millions. You can fit 109 Earths side by side across the diameter of the sun. So you could do a little bit of quick math and figure out what that would be in the whole volume. But it's on the order of millions of Earths inside the sun. 1.3 million. Thanks, Dave.
There
any more questions in the Q&A? I don't have the Q&A open here, so if you want to.
Well, one question is whether we need to worry about our sun dying or exploding or imploding or.
That's a great question. Yeah, because we talk about the sun exploding, and so you think that would, perhaps be disastrous for us. But thankfully, that's not something that we have to worry about anytime soon. So the sun has been around for about 5 billion years. and it is likely to live for about 5 more billion years. So it's about halfway through its life, and we have a very, very, very long time before it is going to start to die. So that's not something that we need to worry about anytime soon, thankfully.
Okay, well, I think we should probably wrap up. Thank you so much for talking with us, Claire Raftery, and thank all of you for coming. If you can, please answer our short survey about the webinar. I think it's like 4 questions, and definitely head over to www.solarweek.org to ask. For the rest of the week, solar scientists will be on answering your questions about the sun, and our solar week will finish on Friday. We'll go through Friday, and then we'll see you again in October because we have it twice a year. So thanks so much, everybody.
Thanks everybody for joining us. There's a question about the survey. The link for the survey is on the top of the slide up here on the top right. I will get this survey for you now.
Survey's in the chat now. Oh, it says, is that a L or a capital I in the link?
It's an L, so it's bit.ly/2u. Oh, that's a good one. Actually, I don't know if that second one is an L or an I. I think it's an L.
That's a good point.
It's an L, so there's 2 L's and no I's. You should be able to just click the link here and it hopefully will take you in. I don't actually know, Laura, why Solar Orbiter is black. It may actually just be the way the picture is, the picture in the graphic that we have. Of course, color plays a really big role in thermal properties. So, you know, black, it's both good at absorbing heat, but also very good at rejecting heat. And so it's a good way of trying to keep the thermal properties stable. It's another reason why we've painted the Inouye Solar Telescope white, because we want to try and keep as much of the excess temperature away as we possibly can. So it's a good stabilization. And for the same reason, they put gold foil on the spacecraft. So the gold foil is called mylar, and it's a very specialized foil to try and maintain, again, to try and maintain the thermal stability of the different components, and especially when it comes to electronics and things like that, that you need to they need to be maintained sensitively. That all needs to be protected.
Someone is asking, Jenny McCall is asking, will we have access to the presentation to share in our classes after today? Yes, you will. We will put it at www.solarweek.org on the top page once we finish processing it. And she says, amazing. And we have archives of all our past live webinars there as well. There's actually a link on Solar Week that says past webinars, and you can look at all those too. Of course, they're not live, but got some great presentations.
Tony, your question of why did Parker Solar Probe disappear in 2027? I don't know if that might have just been the way it was played, but that shouldn't be the case. Let me see. Let's fast forward to 2027 and see.
Oh, yeah. Okay. So Brian also says the YouTube live stream will be visible on our YouTube channel immediately following the meeting. So that's great too.
Tony, to answer your question, I don't know that I can, I don't work for the Solar Probe team, so I don't have a good, like a fixed answer for you, but my guess is that the mission is only scheduled through 2027, and so they just haven't planned into the future. But I don't think that means it's going to disappear or anything like that. I think they will, they'll figure out what the next phase of the mission will be.
All righty. Shall we exit?
Sounds good. Thank you, everybody.
Thanks so much, Claire.
Stay well.
Really cool.